So we started talking about alkanes and how to properly name alkanes. And again, really how we name alkanes is very similar to how we name everything else. But just to review again, different aspects of it, always pretty much when you're naming an organic compound and you have the formula given to you, you always again want to find that longest continuous carbon chain. And remember, it does not have to be the straightest. Again, it could kind of go straight, go up and go over, or go down and go over and stuff like that. But again, here we want the longest carbon chain. That for an alkane will give you the base of the name, which is again going to be one of those kind of 10 alkanes we talked about. Once you do that, pretty much everything else attached is going to be groups that are attached. Remember, groups are essentially alkyl groups, which are really carbon-containing groups, also based off of the first 10 alkanes, except that they are missing a hydrogen to allow them to connect and not give carbon too many bonds. So, for example, if we had a CH3 group, that's based off of one carbon, which is based off of methane. And again, because it's a group, we kind of drop the last part there, and we call it a methyl YL group. To go with our alkyl groups. If we have halogens or anything like that, they're fluoryl, chloral, bromol. Once you do that, the next thing you want to do is number the chain to give the groups the smaller number. And lastly, kind of put everything together about location. A couple of things we talked about, again, between a number and a letter. We do a dash between two numbers. We do a comma, and we do go alphabetical regardless of prefix, the groups, and also regardless of number, and put them together. So again, if we had something, maybe like this. All right. So again, we would want to find our longest continuous carbon chain. And again, there's a couple of different ways we could count. Let's go with straight across 1, 2, 3, 4. We go straight across 1, 2, 3, 4, and then go up 5, 6, which is more. We could also go 1, 2, 3, and then down 4, 5, 6. So that is the same. We also have 1, 2, 3, 4, 5, 6, 7. So actually, this is the longest carbon chain in this case. Again, 4 straight across, 6 up, 6 down, and obviously 1, 2, 3, 4, 5, 6, 7 would give us our longest carbon chain. So as we talked about, you do want to kind of try all of your options there. And it actually, this would be our longest carbon chain of 7, which gives us the base of the name of, if I could write it there, heptane. That means that we actually have a 2-carbon group attached to it. 2 carbons is based off of ethane. Is missing a hydrogen to make it a group, so it becomes an ethyl group as we get rid of that. So we have an ethyl group there. And now what we want to do is figure out what is the numbering for that ethyl group. And we can, again, number 2 directions, going right to the left, I guess. 1, 2, 3, 4, 5, 6, 7. We could also go the other way. See if there's any difference. We go this way. 1, 2, 3, 4. 5, 6, and 7. So in this particular case, it does not matter which way you go, as either way gets you 4, which would be the lowest. So putting that together there gets us 4 ethyl and heptane. Any questions on that? We also, I think, talked about isomers last time. Remember that isomers basically have the same formula, but different arrangements. So again, if you took just a 4-carbon compound and just attached them straight across, that would be butane. We could then go, if you wanted 3 carbons, and put 1 carbon up on top. And as we talked about, this here, longest continuous carbon chain is only 3, which would give you propane. And we would have 2-methyl propane. These are 2 different names, and they are 2 isomers of each other. They both have 4 carbons and 10 hydrogens in each of these cases here, and that makes them isomers of each other. Any questions on any of that stuff we talked about, I think, last time? Okay, so let's continue on here. Okay, so as we also talked about, I think last time as well, kind of during discussion, I think for both everybody, when we do have the name, you always want to kind of work your way backwards. So if we were to draw this name here, which is 1-chloral 1,2-dimethyl heptane, the key is really to work this way, sort of backwards. So we would start with the first one there, which is heptane. Heptane will tell us that it is 7 carbons. So really that's all you want to kind of lay up is the 7 carbons, nothing else, just the carbons. 1, 2, 3, 4, 5, 6, and get the right number there. We'll go with 7. That takes care really of the heptane. 1,2-dimethyl. So di means, as it says here, 2. So within this compound, there are 2 methyl groups, and they are carbons 1 and 2. And as I mentioned, I think last week as well, since you are drawing, you could really number it whichever way you want, left to right or right to left. I personally, just for reference sake here, I'm going to go with that being number 1 in terms of my carbon, which means if that is number 1, I should have a methyl group hanging off of it. That means right next door should be carbon number 2, which also should have a methyl group hanging off of it. That takes care of that part of the name. That lastly leaves us this part of the name, which is 1-chloral. That means at carbon number 1, I have a chlorine attached to it. That takes care of that part of the thing. What is left again is to make sure carbon ends up with 4 bonds. And what we do for that is we basically add hydrogens, however many we need to get carbon to 4 bonds. So if we look at carbon number 1, it has 3 lines coming in, which means it has 3 bonds. That means it needs 1 hydrogen only. Carbon next to it also has 3 coming in, which means it needs 1 hydrogen as well. Carbon next to it has 2 lines coming in, which means it needs 2 hydrogens. Same thing for the next guy, same thing for the next guy, and same thing for the next guy. Guy at the end has only 1 line coming in, which means to get the 4, he needs 3 hydrogens. And there you go. That would be the structure there. This obviously would be the condensed structural formula as it shows there. Any questions on that one there? Yeah. All right, so why don't you give this one a go, draw the condensed structural formula and the line structure for 3-bromo 1-chloral butane. So take a second here and see what you come up with. Backwards here in terms of the name. So starting in the back part of the name here, we have butane. That tells us that is 4 carbons. So again, we just want to start with the 4 carbons, nothing else. Leave a little room in there. There's 4. That takes care of that. We have on carbon number 1 a chlorine. So again, personally for me, I'm going to go left to right, left being carbon number 1. So that is where I will put my chlorine. That takes care of that. Now that I chose this as carbon number 1, clearly everybody else needs to be numbered accordingly, which means carbon number 2 would be next door and 2 down would be carbon number 3. And that is where we should put a bromine at carbon number 3. At this point, we're out of everything else. So all we need is a hydrogens. Guy at the far end here on the right needs 3 hydrogens to get to 4 bonds. Carbon next to it has actually 3 bonds, which means just needs 1. Carbon next to it has 2 bonds, just needs 1. And our number 1 carbon here would need 2 in this case. That would be our condensed formula. Our line formula would be basically for carbons. So it looks something like this. Will work. We got 1, 2, 3, 4 carbons. Again, here, I'm going to attach this as carbon number 1. That means that that's 1. I'll put a circle. You don't need to put the circle. That's carbon number 1. That'd be carbon number 2. Carbon number 3 would be here, which would be a bromine. So it looks something like that. Or, you could start like this. Might be another way it might look, could look like this as well. Any questions on either of those? Okay. All right, let's try a couple more here. Name each of these. So see what you come up with. Okay, let's take a look here. Just move a couple of things on my screen so I can see. Let's do that. All right, so again, we want to go longest continuous carbon chain. Let's take the first one here. Looks like we're just going to go straight across here. That's 1, 2, 3, 4, and 5. So that is definitely 5 carbons, which is obviously the longest continuous carbon chain. That is going to give us a base of our name of pentane. We clearly have a chloral group here hanging off. So what's left is to number. So we could go left to right, which means that's carbon 1, carbon 2, carbon 3, carbon 4, carbon 5. Or obviously we could go the opposite way, starting here at carbon 1, carbon 2, carbon 3, carbon 4, and carbon 5. Clearly going right to left gives the chlorine a smaller number, which is 2, and that would be the way we want to go. So that's a little 2-chloral pentane. Any questions on that particular name there? All right, so let's take a look here at the next one. We could go 1, 2, 3, 4, 5. We could also go maybe 1, 2, 3, 4. So that's short. We could also go 1, 2, 3, 4, 5. And I think that would be it. So let's get 5 really is our longest. So might as well, again, if you have the option, just take the straightest. So that is 1, 2, 3, 4, and 5. Again, this is going to give us pentane here as our base. In this case, we have 2 groups hanging off, one here and one here. So remember, when you just see a line, inline structure, there is at the end of it a carbon and would have 3 hydrogens. So these are actually methyl groups. And there are obviously, as we can see, 2 methyl groups in this guy. So we got a dimethyl situation happening. We now want a number. So if we go left to right, that is 1, that is 2, that is 3, that is 4, that is 5. And if we go right to left, in this case, that would be 1, that would be 2, that would be 3, that would be 4, and that would be 5. So going right to left, we end up with a 3 and a 4. Going left to right, we end up with a 2 and a 3, which means we would want a number in this direction. as that seems to give us our smaller numbers, which would be 2 and 3. And that means we have everything we need, I believe, in this case. So putting all that together, that's going to be 2, 3, again, a comma between two numbers, dash dimethyl for the 2 methyl groups that are in the compound. And lastly, our pentane there at the end. Any questions on that name there? Okay. Let's see here. Why don't we try a couple more here, maybe? So I'll do it here, actually. I'll just throw it here. All right, so why don't you, let's see. Why don't you give the name for these? So let's do CH3, C, CH2, CH2, CH3, Cl, and CH3. And then let's do that. So give the name for each of those, and then why don't you draw the structure for, let's go with propyl cyclobutane. And why don't you draw, let's go 2, 2, 4 trichloral pentane. All right, so name up on top, draw the guys on the bottom, see what you come up with. Okay, let's take a look. So we'll start at the top here, looking for the longest continuous carbon chain. So again, we could just go straight across 1, 2, 3, 4, 5. We obviously could go 1, 2, 3, which is less. We could go 1, 2, 3, 4, 5, which is 5. So it looks like a couple different ways you could get to 5. Might as well again go with our straight across. So that is going to give us the base of our name here, which obviously would be pentane in this case. We have basically a chloral group hanging out over there. We also have a 1 carbon group, which is a methyl group hanging there. And in this particular case, you could probably tell that numbering left to right looks like the move. 1, 2, 3, 4, 5. That gives our groups a number of 2. Obviously, if we went right to left, we would end up at number 4, which is obviously larger. It's always smaller numbers here. So that's going to be a 2 chloral and a 2 methyl alphabetical first, going with C before M, gives us 2 chloral, 2 methyl. Let's see if I can hook it up there. There we go. Pentane in that particular case. Any questions on that name there? Next one, we got a cycloalkane, and our cycloalkane here is basically a 1, 2, 3, 4, 5, 6 member ring. So 6 member ring is based off of hexane. It's a ring structure, which means it becomes cyclohexane. And that means that we do have 1 group hanging off right there. That is a 1, 2 carbon group. Right there, 2 carbons. And that means that is a ethyl group. So this would be just ethyl. I didn't draw the other part. So be ethyl-cyclohexane. Any question? Again, you don't need a number here because it's the only group there. which would imply that that is carbon number 1. Any question on those two names? All right, so drawing our guys here, going backwards. Butane, again, is 4. So we're going to do our 4 carbons. Takes care of that. This is cyclobutane, which I guess I should have read first. That means these 4 carbons are actually connected. So real or not, that is going to be cyclobutane, which is our square. Again, a carbon at each corner is 4 carbons, and propyl is 3 carbons, which would be something like CH2, CH2, CH3, as I squeeze it in there. Want to go all line, it would look something maybe like this. 1, 2, 3 carbons sort of happening in this particular case. Any questions on that one? If you wanted to do the condensed formula on that, that would look something like this. Looks something like that. All right, last one here is pentane. So again, that would be 5 carbons. Takes care of that. Trichloral means we have 3 Cls basically there. And they are at carbon number 2, 2, and 4. I'm going left to right. So this is carbon number 2 for me, which has a chlorine there and a chlorine here. And that's 3 and 4 would have a chlorine. Everybody else going to be hydrogens. And in this case, it doesn't need it, but we do need right there. Any question on any of those naming or drawing these alkanes? Let's talk about some properties of alkanes. Different uses of alkanes and their compounds result from their physical property. Solid alkanes make up waxy coatings, like we kind of see here on our apples, to help inhibit mold and enhance appearance. Alkanes with 1 to 4 carbons are typically gases at room temperature. So that's our methane, ethane, propane, and butane. That is 1, 2, 3, and 4 carbons. Butane has 4 carbons. Alkanes with 5 to 8 carbons are highly volatile liquids at room temperature and making them useful in fuels. Volatile means that it goes into the gas phase pretty easily. Like open it up and pop is going to go basically into the gas phase. Octane, like your gas, 8 carbons basically involved in there. Alkanes with 9 to 17 carbons are liquids with higher boiling points. They are typically using those dispersion forces, which are really weak, but they have a lot more carbons, so they do sort of have higher boiling points, and are what motor oil, mineral oil, kerosene, jet fuel are. Decane is 10 carbons. In fact, how you get something like gasoline is you take a big old long chain of an alkane and basically do as sometimes referred to as fracking, which basically means you break it apart into smaller fragments like octane and so forth that can be used as various types of fuel. When we get alkanes that have a lot of carbons, 18 or more, they're kind of waxes at sort of normal temperature, and things like petroleum jelly or Vaseline, again, are usually somebody that has like 25 carbons involved. Alkanes are definitely non-polar. They basically will use, as I mentioned before, because of that, they will use dispersion forces. And if you remember, those dispersion forces are relatively weak type of intermolecular forces. They're insoluble in water. So typically, again, they kind of float up there on water. That's the organic layer. That's usually the water layer. They're flammable in air, found in crude oil. And again, they really don't mix well with water. Again, water being polar, and obviously a lot of alkanes are non-polar. So there's that idea I think we talked about of like dissolves like. So in this case, you know, a polar and non-polar guy are not going to be soluble in each other. And again, because our polar guy is going to try to use some type of dipole-dipole hydrogen bonding, our non-polar alkane is going to be basically using dispersion forces. And that means that they have no way to keep that interaction going for a long period of time. And like in an oil spill, we typically see the oil kind of float up there on water. Now, alkanes do go through some reactions. Alkanes will go through a combustion reaction, and a typical organic combustion reaction. This is kind of what happens when you light the Bunsen burner. A little methane, a little O2 from the air, and a spark gives you fire, and you make CO2 and water. This is your classic organic combustion reaction. You see O2 on the left-hand side, always sort of producing CO2 and water if it's a complete combustion. So those are the key points there. Obviously, you get a lot of heat and energy coming off of there. That is butane, same idea, combustion reaction. We got O2, CO2, and water, and obviously our organic guy that we are starting with. The little triangle on top of the arrow here means heat. When you see that on top of the arrow, that's basically what that means. Obviously, you might be familiar, obviously, with propane used in barbecues and so forth. Obviously, also a combustion reaction here. We could balance these like we normally would a regular equation. Want to make sure we have the same number of guys on both sides of the arrow. So very common alkanes will go through this type of reaction. Another type of reaction, in addition to a combustion reaction, that alkanes will go through are what are referred to as substitution reactions. And in a substitution reaction, what essentially happens is a substitution occurs, which means basically we're going to take off a hydrogen in our alkane, and we're going to substitute in a halogen for it. So in this type of reaction, we typically will take an alkane, we'll react it with a halogen, Cl2, Br2, and so forth. Maybe a little bit of heat, maybe a little bit of light or UV involved. And basically what will happen, for example, is, let me actually come here and do it, but more room to draw. Let's just say we had a simple alkane here. And let's basically react it with bromine, which is Br2. So basically what happens in this case is we could look at these hydrogens, and every single one of these hydrogens are what are referred to as being equivalent. They're the exact same, which means technically you could do this reaction with any single one of these hydrogens you want. It doesn't really matter. You could choose any one you want. I'm going to personally just choose this guy right here. So this is the hydrogen I'm going to choose. And what's going to happen is that hydrogen right there is going to basically come off. And one of these bromines here will come on basically in its place. And this is the substitution part. We're going to take out the hydrogen and substitute it in here for a halogen. And this guy is going to come on. Put the right thing there. This guy is going to come on. And the result of that is we will end up with, and this is really important when you're drawing sort of the products of these reactions. Sometimes people want to go crazy and draw all kinds of weird things when they're drawing products of reactions. And for the most part, they're fairly straightforward and simple. And what I mean by that is there's really only usually one part of the molecule that changes. Everything else remains exactly the same. And what I mean by that, in this particular example, every single part here that is left, we'll go with this sort of color. This guy, this guy, this guy, this guy here in blue. Absolutely, positively, nothing changes with that. So you literally can just copy it exactly the way it is. Absolutely nothing should change. The only thing that changes is our bromine will now come on there at the end. So we will put our bromine on right there. What else happens is the hydrogen comes off, and we also have one more bromine. So those two guys come together, and that's basically going to be H plus and Br minus, and that will make HBr. So we get this alkane where we get a substitution reaction. You can substitute any of the hydrogens. And again, that is where that comes from those two guys there. This is what is sometimes referred to as the mono-substituted product, which is usually what you want to draw. And that's a big fancy word for where we just took one hydrogen off. In reality, if you let this go, you probably could replace every single hydrogen that's there, but with a bromine, but we will just usually do just the kind of first hydrogen in this particular case. Any questions on that there? Also, very similarly works the same on a ring structure. So if I took this plus some Br2, same thing's going to happen. Again, even though it's sort of line structure here, there actually is two hydrogens at every single carbon. So one of these hydrogens is going to go off. One of these bromines is going to go on. And again, absolutely everything stays the same. So all I have to do is redraw this structure here. Nothing opens up, and basically put the Br there. And obviously the hydrogen that came off would hook up with the other Br and make HBr in this particular case. Any questions on that there? So this is a substitution reaction for alkanes, and they basically undergo these guys where they replace a hydrogen with some type of halogen. Any question on alkanes? Okay. Then let us talk a little bit about alkenes and alkynes, which are the next couple of organic groups. Alkenes are double bonds, which means they have a double bond somewhere there. They have a general formula of CnH2 times N. So if you remember, alkanes have CnH2 plus 2. Alkenes, because they have a double bond, lose 2 hydrogens, so they end up with that formula. Alkynes have a triple bond happening there, and they have a general formula CnH2n minus 2. So these are what are referred to as being unsaturated, because they do not have the maximum number of hydrogens available. So to sort of see the relationship here, let's just look at the simplest one we could have. Let's start with our alkane, 2 carbons. This is ethane, ANE, CnH2n plus 2. We're going to double bond the center. When we double bond the center, we lose a hydrogen from each carbon, and that ends up giving us something that looks like this. This is ethene, ENE, because that's a alkene, ENE, has a general formula CnH2n, lost the 2 hydrogens as we made that double bond, and then make a triple bond here in the middle. We're going to lose 2 more hydrogens, and we end up with this deal. This is surprisingly known as ethine, YNE, hence the YNE part of the name here. And this is CnH2n minus 2. Any questions on either of those surnames? As you could also see, these guys are also based off of the first 10 alkanes, but they do have a double bond or a triple bond, which again means that they are unsaturated hydrocarbons because they are not containing the maximum number of hydrogens that should be there. And that's what this says here, unsaturated hydrocarbons, because of those double bonds or triple bonds. So alkenes, again, will have 1 or more double bonds in there, carbon-carbon double bonds. And again, to maintain carbon only having, again, 4 bonds, we have to get rid of those hydrogens. And again, the way we get rid of them is essentially, as I mentioned, hydrogen from each carbon is lost in that process. So remember, as you essentially put on another bond in organic chemistry, you sacrifice basically 2 hydrogens. It also changes in an alkene the sort of geometry that we see. Now, when we look at, say, this carbon here in the center, it has 1, 2, and 3 electron pairs. And it also has 1, 2, 3 bonds. The geometry of this guy, unlike an alkane, which is tetrahedral, the geometry here is trigonal planar. That's our triangular type thing. That's our 120 degrees unilateral sort of triangle, as you could kind of see here. Triangle happening on both sides in this particular guy. Some alkenes, ethene, also called ethylene. The kind of more formal name is obviously ethene. Important plant hormone, ripening fruit like bananas. Also breaks down cellulose in plants. When we look at something that's an alkyne, again, we're looking at something that has 1 or more triple bonds in it. Simplest one you could have, obviously, is 2 carbons. So you can make that triple bond just like our double bond happening. And again, a consequence of our triple bond is 1 more bond on, 2 more hydrogens lost, and also some different geometry here as well. So 1 electron pair, 2 electron pairs, and 2 bonds. That gives us now a more linear geometry, 180 degrees straight across. Any questions on that there? So how do we go about naming these guys? We basically follow the same rules as we do with alkanes, but there's a couple of different things. We are looking for now the longest carbon chain, but it needs to contain either the double bond or the triple bond, depending on which one's present. It needs to contain that. That will still give us the base of our name, which we will now change to either ENE if it's a double bond, or YNE if it's a triple bond present. We then will still find our groups that are attached. And now something that's a little bit different than what we do with alkanes is when we number the chain, we want to number the chain to give the double bond or triple bond the smallest number. So it's no longer the groups which are important here in a sense, in terms of the numbering. We want to go whichever way will give our double bond or triple bond the lowest number. Now, if you do run into a situation where no matter which way you go, left or right, the double bond or the triple bond is located the same carbon, so like carbon 4, no matter which way you go, then the next thing you would look at is groups. So you kind of follow that order. Double bond, triple bond takes priority. If there's really no difference between which way you go for those guys, what will help you decide which way you should go is then the groups, whichever one would give the groups a smaller number. We actually do need to give the location of the double bond or triple bond in the name. So much like a group, we have to tell people, hey, at carbon number 2, that is where our double bond or triple bond may be. So we actually give the double bond or triple bond a number. And this is usually if we're about probably like 4 or more carbons, you would give sort of the double bond or triple bond an actual number. And whichever way you number, again, to give the double bond or triple bond the smallest number, that is how you number all the other groups that are attached. So let's take a look here, kind of go through here and sort of see what's happening and sort of the process here. Again, we're going to be looking for the longest continuous carbon chain. In this case of A, we're looking for obviously the one that contains the double bond. So that is 1, 2, 3, 4, 5, 6, 7, 8 carbons coming through. So this guy has 8 carbons. 8 carbons, which is based off of octane. Here we do see a double bond happening, which means our octane now becomes our octene, ENE. Now we need a number to give where that double bond is located. If I number left to right, this is carbon 1, this is carbon 2, this is carbon 3, carbon 4, carbon 5, carbon 6, carbon 7, carbon 8. Going this way, my double bond starts at carbon number 3. If I go the opposite way, 1, 2, 3, 4, 5, 6, 7, 8. If I go the opposite way, my double bond starts at carbon, not 8, bad counting, my carbon number 5. 5 is larger than 3, which means we actually would want a number in this direction. So putting that together, number 3, this is 3-octene. Octene, ENE, tells us it's a double bond. Octane tells us it's 8 carbons, and that double bond is located at carbon number 3. Any questions on that one there? Let us take a look at the guy on the bottom here. We got 1 carbon, 2 carbons, 3 carbons, 4 carbons, 5 carbons, 6 carbons, 7 carbons. Oh, that was pretty bad. 1, 2, 3, 4, 5, 6, 7. Other option would be go this way, contain double bonds. So 1, 2, 3, and then down 4, 5, 6. Looks like either way you go, you are going to, maybe I miscounted and try that again. This is 1, 2, 3, 4, 5, 6, 7. That's good. Going down is 1, 2, 3, 4, 5, 6, 7. So we do get 7 no matter which way you go. If I learned how to count, that would be good. So that is 7. Looks like actually a winner here. So 7 carbons, we'll take the straightest to make it a little bit easier. 7 carbons is based obviously off of heptane. We see actually here a triple bond. So we go from heptane to heptine, YNE, to give us a triple bond. We also have a group hanging off of here. This is a 1, 2, 3 carbon group. 3 carbon group is based off of propane. Drop that, becomes a propyl group. And now we need to give the number of where our triple bond is. So this is going to definitely be the lowest number, which would be 1, 2, 3, 4, 5, 6, 7. 8. Should learn how to count here. Let's see here. We got sorry, I missed one there. There's 8. There you go. That's even better here. Let's go with octine here. Sorry about that. So octine. It's good I numbered it, I suppose. So 1, 2, 3, 4, 5, 6, 7, 8. There we go. And then we got our propyl group. So that is going to be carbon number 4, because we need to go this way here for our triple bond to give the smallest number. So that means that number 4, we have a propyl group. Now putting it together here, counting correctly for propyl octine. Any questions on that one there? So it actually is 8 here. So 8 going across, and then 7 coming down. All right. So let's take a look at these things again. As I mentioned, very similar. We just want to kind of change our ending. These guys here, ethene and ethine, no need for numbering of the double bond or triple bond, because there's really only one location where they could be. It's got to be here. And so basically about 4 or so carbons is really where you should start giving the name or the number for the location there of your double bond or triple bond. All right, so why don't you try these couple here and see what you come up with. So give the names. Okay, let's take a look here. So let's see. Let's go straight across. So that is 1, 2, 3, 4, 5. And again, if we went the other way, 1, 2, 3, and then down. So 1, 2, 3, 4, 5. Looks like 5 is a winner. If I counted correctly this time, no matter which way you go. It obviously has a double bond happening here. So that is going to make us go from pentane to pentene, ENE, for the double bond happening. We also have a group hanging off of here, which is a methyl group. And we want a number to give, again, the double bond the priority, which means we should go left to right here. 1, 2, 3, 4, and 5. That means our double bond's at carbon number 2. So this now becomes 2-pentene for the location of the double bond. And because we locked into place numbering in this direction, that means that our group there is at carbon number 4. So that will be, I'll erase a little bit here so I can write it, maybe right about there. Again, that will be then 4-methyl 2-pentene. Any questions on that name there? All right, coming across here on the next one, not a lot of options there. So it's 1, 2, 3, 4, 5, and 6. 6 is based off of hexane, ANE. We see a triple bond happening there. So this becomes hexine. And the location of that triple bond, we would go right to left. So that's 1, 2, 3, 4, 5, 6. So that's carbon number 2, which would be 2-hexine. Any questions on either of those two? And again, condensed formula, you're looking, again, this is CH3. C, CH2, CH2, CH3 would be it. All right, why don't you try a couple here where you draw it. So why don't you draw 3-ethyl, 6-methyl, 3-heptene. And why don't you draw, we'll go with 2-bromol, 3-hexyne. And why don't you name this guy here, which is CH2, CH2, CH3, and a CH3. All right, take a minute, see what you come up with here. Again, we have the name, so we're going to just kind of work our way backwards here. So starting with the first one up on top, obviously we have heptene. The ENE tells me it's a double bond. The heptane sort of part tells me it's 7 carbons. So we're going to lay up 7 carbons here. 1, 2, 3, 4, 5, 6, and 7-ish. The 3-heptene tells me that the double bond is at carbon number 3. So for me, I'm going to go left to right. That would be carbon 1, carbon 2, and carbon 3, which is where I will put my double bond. That takes care of basically the back end. Because I went left to right in my case and made this carbon number 1, I have to keep that for everybody else, which means that carbon number 6, there should be a methyl group. So carbon 1, carbon 2, carbon 3, carbon 4, carbon 5, carbon 6. We'll squeeze it in up here, maybe. Takes care of our methyl group. And at carbon number 3, there would be an ethyl group. 1, 2, 3. Ethyl group is a 2-carbon group. And again, everything else here is going to be hydrogen. On the left here, we need 3. We need 2. We need none in this case for the next one. This guy just needs 1. This guy needs a 2. This guy needs 1. And this guy here would need 3. Any questions on that one there? Looking at this one here, YNE tells us triple bond. Hex tells us 6. So we'll lay up our 6 carbons. Again, the 3 tells us triple bond at carbon number 3. I am again going left to right, which is 1, 2, 3. And I'm going to put my triple bond in there. That takes care of that. Because I went left to right, that means that this would be carbon number 2. And that's where my bromine would go. And in this particular case, everything else is going to be hydrogens. Carbon here has 4 bonds. Carbon here has 4 bonds. This guy's got 2, and this guy's got 3. Any questions on that one there? All right, lastly, going straight across here, 1, 2, 3, 4, 5 carbons. Going straight across and up, 1, 2, 3, 4. So it does look like 5 straight across is a winner. That is going to be based off of pentane, going to become pentene because of the double bond. Double bond is going to be at carbon number 1 there, which is where I got 1 pentene. That would be 2. That would be 3, where we have our methyl group, and it would be 3 methyl, 1 pentene. Any question on how to name alkenes or alkynes or draw them? Obviously, you need to be able to do both. Okay. Then let us talk about cycloalkenes. So cycloalkenes are also based off of our cycloalkanes. Remember, those are kind of like our geometrical shapes, like our triangle, our square, and so forth. These are basically that is a, I guess, drawing there. Let's go that way. Maybe try to straighten it out. Obviously, our 6-member guy here. These are these guys basically with a double bond in there. And if we have a double bond, we do number the substituents that are attached based on the double bond location. So the double bond location is always going to be carbon number 1. But there's an important thing when you are, for example, have a double bond. You could number one of two ways, but the deal is you got to go through the double bond, which means that would be one, that would be two is okay. This would be one, and then this would be two. That's okay, because you're going through the double bond. What would not be okay is if you went one and went away from the double bond. So you cannot number that way. You have to kind of go through the double bond when you're numbering. So if we look at this guy here, that is 1, 2, 3, 4, 5 carbons in a ring structure is cyclopentene, ENE, because of the double bond that's here. Now, to number the group that's there, which is our methyl group, we have two options. We could go like they did, 1 and then through the double bond, 2 and 3. The other option would be start here at carbon 1, go through the double bond, which would be 2, 3, 4, and 5. Again, we're looking for the smallest number, which means numbering in this direction is the correct way, and that is how we get to 3-methyl cyclopentene. So you always want to make sure that you do number and go through the double bond on your numbering. You can't go away from the double bond there on your numbering. Any questions on that there? All right, so why don't you name these two guys here? Let's see what you come up with. And why don't you also, while you're there, draw, let's go with 3-bromyl, 1-methyl cyclobutene. All right, so draw that guy and name these guys here. All right, let's take a look here. We'll start on the left, and clearly that is a ring structure. That is 6 carbons. Again, you could just count the little spots there. Maybe if it writes, there's 1. That's 2. That is 3. That is 4. That is 5. And that's a 6. That is based off of cyclohexane. There is a double bond there on the right, which then makes it cyclohexene, ENE. And that is all she wrote on that one. There's no other groups attached. You don't need to give the number for the double bond in a ring structure because it's assumed that this would be carbon number 1, no matter where it is. So no need to actually give the location in a ring type structure. Any questions on that name there? Same thing here. Really, the biggest carbon chain is our ring structure, which looks like in this case, we just put some circles around it. 5, which again is based off of cyclopentane. We again do see a double bond. So this becomes cyclopentene. We have a line here, which again is our methyl group. Remember, carbon at the end there with 3 hydrogens. And same thing here, another methyl group. That is 2 methyl groups in this compound, which gives us a dimethyl situation. We need to give some names. So we have really 2 choices here, remembering that we want to make sure that we do go through the double bond, which means we could start here and call that carbon 1. Going through the double bond would be 2, 3, 4, and 5. Now we can start on, we'll start on the inside here. Starting here as this carbon 1, this would be carbon 2, carbon 3, carbon 4, and carbon 5. In this particular case, obviously we see the red way gives our methyl groups the smaller number, which is 3. Happens to both of the methyl groups are on carbon number 3. Remember 3, 3, comma between 2 numbers, dash our dimethyl and our cyclohexane. Pentane. Any questions on that name there? All right. Lastly here, 1-methyl cyclobutene. Cyclobutene is based off of 4 carbons. ENE means there is a double bond, so I'll just draw the 4 carbons as a square. And I'm just going to put my double bond in right there. And that means that this technically could be carbon 1, and this would be carbon 2, and I'll number this way 3 and 4. That means at carbon number 1, there should be a methyl group. So I could just throw a line going up here. If you want, you could do the CH3. And at carbon number 3 would be the bromol group, which would be over here. Any questions on that one, or how to name cycloalkenes? Now, when we do have a double bond situation occurs, what ends up happening is we get a sort of lock in place of everybody. And what I mean by that is when we have single bonded carbons that has something like hydrogen, for example, this single bond is free to rotate, which means, you know, you could just spin around freely. When we sort of lock our carbons into place with a double bond, it is sort of locked into place, which means we lose the ability for rotation around the double bond. And what that creates is there are certain groups that end up on the same side of the double bond, which is what is referred to as Cis Isomers. And there's some that end up on opposite sides of the double bond, which are what are referred to as trans isomers. So cis isomers means that we're on the same side of the double bond, the group. Trans means we're on opposite sides of the double bond. And there is a certain thing that has to happen in order for a cis or trans isomer to even exist. So not in all cases does a cis or trans isomer exist. There has to be basically a couple things that happen. So for example, you need a double bond, obviously. And within the double bond, on one of the carbons, say on the left, you need to have different groups. So these two things need to be different. So we'll go over here, A, and we'll go D. These groups on this carbon needs to be different. So that's the first really major thing that you need to have is on each of the carbons within the double bond, they need to have different groups. Now, hydrogen can even be considered a group in this case, but they do need to be different. The other thing that you need to have is a group that's on opposite carbons that are the same. So you need a group like these two guys that are on opposite carbons that are the same. So let's take a look at the couple of examples I got on the bottom here. Here we go. We have our double bond, which is what you want to focus in on. And when you focus in on the double bond here, first thing you want to check is this guy and this guy different? The answer is yes. And we want to check this guy and this guy. Are they different? The answer is yes. So that's good. We then want to look for a group that's the same on opposite carbons. And in this case, we could look at the chlorine, could also look at the hydrogen. And in this particular case, we see the chlorines on the same side of the double bond, which means this is a cis. I kind of wrote over it, but it is a cis isomer. We do the same thing if we look at this guy here. This guy and this guy are different. This guy and this guy are different. And again, our chlorine now are on opposite sides of the double bond. And that would be our trans isomer. The only difference is we just add cis or trans to the name. And that sometimes will help us decide, which one we're trying to draw or see. Any questions on that there? Now, for example, if we had this, this would not be possible. Cannot have a cis or trans in this case because this guy and this guy are different, which is good, but this guy and this guy are the same. And because on this particular carbon, it has the same groups, that automatically disqualifies the cis or trans from being possible. Any questions on that? Obviously, the cis and trans are isomers, which means just like before, they have the exact same molecular formula, but different connectivity in that case. All right, so in a cis or trans isomer on the same side, in this particular case, this is our double bond. This group and this group are different. This group and this group are different. These two groups are the same, and they're on the same side, which tells us this is cis. Same thing here, looking at our double bond. Again, different and different, different and different. Same on opposite sides, again, giving us our trans isomer. Here it is sort of in line structure. This again is our carbon-carbon double bond. And here we see our bromine and bromine are on the same side. By the way, the other group that's there is actually a hydrogen in this case. And we see the same side, which would be cis. Here, again, our double bond happening here. There is a hydrogen here and a hydrogen here. The bromine is on opposite sides. And we do see it being our trans isomer in this particular case. Now, if you were asked to draw, this guy like cis 1,2 dibromo ethane, the best thing to do is just to forget about the cis part first and just draw it like normal. So ethane would be 2 carbons, has a double bond, so that takes care of that. Dibromo on carbon 1 and carbon 2 in this case, and then fill in what we need, which would be hydrogens. At this point, you now can rearrange it to make the cis, which is actually what I drew. I actually ended up drawing it as cis. So if we needed the trans version, we could just take this and switch it around by just making one of the bromines down, one of them up. And now we've just drawn our trans version of it. So sometimes it's easier when you're drawing these guys to draw just a regular straight guy structure without the cis or trans, and then isolate the double bond and kind of move the groups up or down, depending on what you're trying to draw. So why don't you take a moment here and name these guys and add the cis or trans to each of these and see what you come up with. All right, since we're getting to the end, let's take a look at least one or so of these guys here. First off, we would just isolate the double bond, which is right here. And clearly we have different groups here and here, which is good. And these two guys are different. The ones that are the same is the chlorines or even the methyl groups. And regardless of which one you choose, they're both on the same side of each other. These guys are on the same side, and even these guys are on the same side. So this is definitely a cis. So let's talk about naming. We're still going to look for the longest continuous carbon chain. And that actually is going to be 1 carbon here, 2 carbons there, 3 carbons there, and 4 carbons there coming through here. 4 carbons is going to be based off of butane with the double bond. That is going to become butene. We want to give the location of the double bond, which is 1, 2, 3, 4, or 1, 2, 3, 4. In this case, it doesn't matter which way you go. It looks like number 2 is going to be where our double bond is going to be located. We also have 2 chloral groups here. So that's going to be dichloral. And we will end up with 2, 3 dichloral. We'll squeeze it this way. 2 butene. And then we would just put the cis in front of it. So we'll clean it up here. 2, 3 dichloral. 2 butene. Any question on that name there? Now, I will say that sometimes when people see it drawn like this with cis or trans, they kind of just focus in on this and don't really find the longest carbon chain. So especially if it's drawn cis or trans, you want to make sure you do find that longest carbon chain and name it accordingly. Any questions on anything we talked about here today? All right, we will lay it up.